A mysterious question from Erdős 26 began as a quiet spark that would travel across decades and disciplines. In 1975, Paul Erdős tucked a puzzle into a corner of a paper, sewing a question about monotone subsequences and maximal sums. 50 years later, the mystery lived on quietly on the Erdős problem page as Problem 1026. On a winter day, a global network of mathematicians gathered, united by curiosity and aided by AI tools. The prompt: could a monotone subsequence problem be cracked not by solitary effort, but by human-machine collaboration? Desmond Weisenberg helped crystallize the idea with a game, Alice and Bob, Coins and Monotone Subsequences. The key question asks, what fraction of all coins can Bob guarantee to take, regardless of how Alice splits them? From there, the idea of Cn arose, the limiting proportion Bob can secure as n grows. Steinkamby showed that if Alice splits into KL2 piles, arranged in K blocks, the longest monotone subsequence has at most K piles. Consequently, Bob can take no more than one kowo of the coins in that construction. Conversely, lower bounds emerge from earlier results, suggesting Cn is not vanishing, but shrinking like 1n and up to constant factors. 2 days of intense thought led to a bold conjecture that CKL2 equals 1K for large K. Then AI entered the stage, with Aristotle and Lean helping formalize the proof within 48 hours. A human counterpoint by Koishi Chan offered an elegant expansion technique, the inflation method. Lawrence Wu connected the problem to a square packing view that makes the sequence Cn behave like a packing ratio. A surprising archival link showed that older papers already contained the essence of the answer. The new synthesis connected weighted versions of Erdős and axis-aligned filling problems. Praeton's embedding argument then tied the general case to the axis-aligned instance that the community had just solved. In parallel, AlphaEvolve produced a numerical path toward the conjectured sequence, revealing patterns in n from 1 to 16. Boris Alexeev then formalized the proof using Aristotle, yielding KL2 1K, a parallel human proof by Steinkamby and a classic inflation method reinforced the result. Google Scholar connected older literature from Wagner and 2016 work to this modern resolution. The story emphasizes that mathematics, at its heart, is a collaborative, tool-augmented human endeavor. A policy note on AI usage in mathematical research highlighted open and transparent collaboration. The final outcome? A complete formula for Cn with upper and lower bounds perfectly aligned. The resolution rests on weighted, axis-parallel square-filling interpretations of classical problems. This blend of human insight and AI search reframes mathematical practice for the future. The fuel behind the breakthrough was the idea that AI can generate new mathematical insights, not merely search. As the proof solidified, the mathematical community celebrated a moment of crossing disciplines and generations. Behind the spectacle lies a simple game about coins, squares, and the shape of optimality. The final chapter shows a perfect match between lower and upper bounds, confirming the conjecture. Epilogue. The era of AI-assisted math has begun, reshaping how discoveries unfold in minutes and hours, not months. The tale closes with gratitude to every contributor and to the Erdős problem site, whose policies encouraged openness. From 1 to 16, from a simple game to a complete formula, the journey was a bridge across time and tools. The numbers reveal a pattern. Cn behaves like 1n and multiplied by a steadily rising factor. Meanwhile, the square packing interpretation gives a geometric intuition for why these bounds hold. In the end, a 50-year-old question found its answer through a chorus of collaborators around the globe. The 48-hour sprint did not exhaust knowledge, but unleashed a new paradigm of discovery. As new techniques emerge, the Erdős landscape becomes richer, with AI as a trusted collaborator.